Pluto, a distant and enigmatic celestial body, was once part of our solar system's planetary family. However, recent alarming statements from prominent astrophysicists like Neil deGrasse Tyson and Michio Kaku have thrust Pluto back into public attention. They have made a startling revelation: Pluto might be on a potential collision course with Neptune. Pluto, once classified as a planet but later redefined as a dwarf planet due to its peculiar orbit, continues to captivate the scientific community. According to recent research by leading scientists, Pluto's trajectory is dangerously close to Neptune's orbit. Renowned astrophysicists like Tyson and Kaku are raising alarms about the potential for a catastrophic collision between these two planets, a scenario that could pose a significant threat to Earth. Unlike any other planet in our solar system, Pluto's journey around the Sun is highly unusual. It takes a remarkable 248 years to complete just one orbit. Since its discovery in 1930, Pluto hasn't even finished one full orbit, which adds to its mystique. But Pluto's orbit is not just slow, it's also highly elliptical, vastly different from the more circular orbits of the larger planets. To complicate things further, Pluto's orbit is tilted at an angle of 17 degrees to the plane of the solar system. This inclination makes its path much more extreme than the other planets, adding layers of complexity to its movement. One of the most intriguing aspects of Pluto's orbit is its interaction with Neptune's orbit. For roughly 20 years of each orbit, Pluto comes closer to the Sun than Neptune does, defying what we might expect based on the relative positions of planets in our solar system. The answer lies in the gravitational influences of other celestial bodies, especially the large planets. The study of Pluto's orbit began shortly after its discovery. Early astronomers were puzzled by its strange path. Unlike other planets whose orbits are somewhat aligned with the ecliptic plane, Pluto's orbit stood out due to its steep tilt and elliptical nature. The realization that Pluto's orbit crosses Neptune's was a major point of scientific curiosity. Despite these irregularities, the stability of Pluto's orbit is a remarkable feature of space mechanics. The phenomenon known as the three-body problem comes into play when studying the movements of Pluto, Neptune, and the Sun. This problem involves understanding how three celestial objects move and affect each other through gravitational forces. Predicting their paths is a complex task, and this is where terms like IML libration, scope libration, and VZK wobbling become relevant. The concept of IML libration refers to the fact that when Pluto crosses Neptune's orbit, it remains at least 90 degrees away from Neptune, ensuring their paths do not intersect. Scope libration describes the vertical movement of a celestial body in its orbit. For Pluto, this means that when it gets closest to Neptune or any other large planet, it is positioned above the plane of their orbits, offering extra protection from potential collisions. Another crucial factor is the VZK wobbling, named after researchers VZ and K, who studied how space objects interact through gravitational forces. This phenomenon explains how Pluto, Neptune, and the Sun's gravitational pulls influence each other, keeping Pluto's path stable despite its apparent erratic behavior. Even though Pluto's orbit may seem unpredictable, this wobbling mechanism helps maintain its steady motion over long time scales. These complex forces help ensure Pluto's orbit remains stable, preventing it from crashing into Neptune or deviating wildly. The three-body problem is essential for understanding how orbits change due to the gravitational influence of multiple objects. Studying this helps us gain a deeper understanding of Pluto, our solar system, and even distant celestial bodies and their stars. Mathematical simulations conducted in the late 1980s revealed that although Pluto's orbit has these stabilizing factors, it is still chaotic. Small changes in its starting conditions could lead to significant variations over millions of years. Despite this inherent chaos, Pluto's orbit remains stable over incredibly long time scales, effectively keeping any potential disruption in check. Recent computer models have provided new insights into how the gravitational influences of giant planets like Neptune, Jupiter, and Saturn affect Pluto's orbit. These models show that Pluto's relationship with Neptune is unique. For every 2 orbits that Pluto completes around the Sun, Neptune completes 3. This relationship helps to stabilize Pluto's orbit. But Neptune is not the only force at work. Jupiter's gravity plays a key role, as does Saturn's, providing additional stability. These simulations demonstrate that Jupiter's gravitational pull alone is strong enough to ensure Pluto remains in a stable orbit for billions of years. Together, Neptune, Jupiter, and Saturn work in tandem to keep Pluto safely on its course, avoiding any catastrophic collisions or other disruptions. These gravitational forces are essential for maintaining order in the solar system. Without them, the system would be much more chaotic, with planets and dwarf planets like Pluto potentially colliding or being ejected from their orbits. Understanding Pluto's orbit is crucial to gaining a clearer picture of our solar system's dynamic nature. Pluto's case serves as a prime example of how even the most seemingly unstable orbits can achieve stability through the intricate interplay of gravitational forces. It also underscores the importance of continuous observation and exploration to better understand our place in the universe. The study of Pluto and its orbit illustrates the unpredictable nature of celestial mechanics. The concept of orbital chaos, which refers to the extreme sensitivity of a body's orbit to its initial conditions, is clearly visible in Pluto's case. Even the smallest change in Pluto's position or speed could significantly alter its orbit over time. Simulations have played a pivotal role in helping researchers understand Pluto's motion. These computer models use complex mathematics to simulate how Pluto and other celestial bodies interact gravitationally. By tweaking small variables, astronomers can see how tiny changes can drastically alter Pluto's long-term orbit. In the late 1980s, these simulations revealed something fascinating about Pluto's orbit. While it may be stabilized by factors like IML and scope libration, it can still be erratic. Even slight differences in Pluto's initial position or velocity can lead to dramatic changes in its orbit over long periods. Despite the apparent chaos, Pluto's orbit remains relatively stable, enduring for billions of years. This demonstrates that while its path may seem chaotic, there is an underlying order to it. Pluto's orbit reminds us of how much is still unknown. Understanding the gravitational interactions of giant planets on Pluto provides important insights into the broader dynamics of the solar system. It reveals how the positioning of each planet can have far-reaching effects, influencing the stability and trajectory of other bodies within the system. Neil deGrasse Tyson, a leading astrophysicist and an influential figure in popularizing the study of cosmology, provides an insightful perspective. Tyson, known for advocating the reclassification of Pluto as a dwarf planet, believes that this shift reflects our ever-growing understanding of the solar system. He does not view Pluto's reclassification as a demotion, but rather as an evolution in our knowledge of the numerous bodies orbiting our Sun. Tyson's approach to celestial mechanics is rooted in continuous learning. He sees Pluto's erratic orbit as a sign of how much more there is to discover in space. The fascination with unknowns, such as the potential for catastrophic events between Pluto and Neptune, continues to captivate scientists and the general public alike. Tyson's predictions about Pluto's future take into account its highly irregular orbit, acknowledging that anything from a close flyby to a catastrophic collision remains within the realm of possibility. Michio Kaku, another renowned physicist, joins the chorus of experts raising concerns about Pluto's long-term future. Kaku, known for his work in theoretical physics, delves into the mathematics behind the potential interactions between Pluto and Neptune. His theory suggests that while Pluto's orbit appears stable today, its future remains uncertain. He warns that over time, even minor shifts in the gravitational forces between Pluto, Neptune, and other planets could lead to a catastrophic event. Kaku's predictions underscore the vulnerability of Pluto's orbit despite its current stability. As we continue to probe the cosmic mechanisms at play, it's essential to consider the future of Pluto's orbit. Although current models suggest that a collision with Neptune is unlikely in the near future, the unpredictable nature of celestial dynamics means that we can never fully rule out such a possibility. Gravitational interactions with other celestial bodies will continue to shape Pluto's trajectory. Even the gradual transformation of the Sun into a red giant and its eventual collapse into a white dwarf could alter the gravitational landscape of the solar system, potentially affecting Pluto's orbit. While the likelihood of Pluto colliding with Neptune anytime soon seems remote, the inherent uncertainty in predicting celestial dynamics over such vast timescales means that anything is possible. The forces at play in orbital mechanics are powerful and intricate. Even the slightest change can accumulate over billions of years, potentially leading to major shifts in the orbits of distant objects.